Welcome to HP Tuner's Ford Gen 2 Coyote Training Part 8. In this training module, we're going to be exploring the PCM Logic Operation. The PCM Logic Operation is going to be how the Ford engineers have designed our Gen 2 Coyote PCMs to actually function and to think. So we're going to be breaking down how things like our air and fuel model work, or how the spark timing is implemented, or how our torque control is implemented. All of this as an overview is needed to be understood before we move into the training course. So as we're breaking down each individual aspects of programming, such as spark timing or torque control or dialing in our airflow models, things will make a lot more sense because you know how everything fits together as a whole and functions to actually make your vehicle run. Without further wait, let's jump in so we can check this out. Okay, so let's get started. We're going to be taking a look at doing an engine control module logic overview in this training tutorial. This is going to be taking a look at and peeling back all the various different layers that we have going on for the programming inside of our Gen 2 Ford Coyote PCM. So this is going to be how Ford has designed the engine control module to work. This is going to make sure that we understand all the various functionalities that are going on. So when we're programming, things will line up and make a lot more sense. So let's first jump in here and talk about the underlying equation that we have that ties together our fuel and airflow models. This is one of the most important things that you can take away from this tutorial. That equation is going to be fuel mass is equal to air mass divided by target air fuel. Now, you may not have heard of the terms fuel mass or air mass. Let's break those down a little bit further so we can make sense of them. Well, mass of any substance is going to be mass is equal to volume times density. So the volume would be, in the case of air mass, something a little bit easier to understand. Air mass, if you look at the volume, that would be the CFM or the airflow coming into the engine. So if we're excluding, trying to factor in the density of the air, that would just be the pure volume of air entering the engine. That's pretty easy to understand conceptually. But then we have this density aspect that we also need to account for. Density is going to be how many oxygen molecules are packed into that volume of air. And it makes a difference because if it's hot air versus cold air, we'll have more oxygen molecules packed into a cold air compared to hot air. And that's because it's more dense. The air is more dense as it's cold. Also, as we change elevation, as our barometric pressure changes, as we move from sea level up in elevation, we'll find that we also have a drop in our density. We have less oxygen molecules packed into that same volume of air. Now, why is this important? Why do we care about air mass? Why do we not just care about the volume of air entering our engine? Well, we have to be able to factor in that air mass in order to determine how much fuel we need to bring into the engine. If we have, let's just say, just taking a hypothetical situation here, if we have a certain volume of air entering our engine, we're at sea level and we're at, let's say, 60 degrees Fahrenheit. And all of a sudden, we take that exact same condition, so we're pulling in the same airflow into the engine, and we move up to 10,000 feet elevation, and we go from 60 degrees to 100 degrees of air temperature. We're going to have a drastic decline or drop in our air density, and therefore, the air mass will be lower. So even though we're pulling in the same volume of air, the air mass will change, it'll be less. Therefore, we would need less fuel. We add fuel in proportion to how much air mass we have coming into the engine. So we need to be able to track air mass, and we do that by knowing both the volume flow and the density. The density is an aspect of both temperature and elevation, so that's all needs to be accounted for. So when we're talking about air mass in our equation of fuel mass is equal to air mass divided by target air fuel, we're going to find that the air mass is going to be measured from our mass airflow sensor. The mass airflow sensor is fitted onto our intake track of our engine. It's going to be measuring how much airflow is being ingested into the engine at any given time. We can see coming up on screen right now, we have a table, which is mass airflow versus period. That's going to be the sampling output from the sensor itself. So we'll find the way this is going to work. It looks up a period or the output from the sensor, essentially the signal from the sensor, and depending on how much that period is changing, that period of time where it's looking at the sampling rate from the sensor, that's going to correlate to different amount of airflow. So that's going to give us the airflow or the volume flow aspect of air coming into the engine. But we're going to be missing that density aspect. And that's where we have an additional table that's used to characterize density. That's going to be our MAF temp compensation versus airflow versus intake air temperature. That's going to further refine and correct the airflow coming from the mass airflow and giving us a total measurement for air mass. So if we have that mass airflow sensor reading, we also have our MAF compensation that will give us the amount of air mass being ingested into the engine. Now, we also have something going on here with our Gen 2 Coyotes. We have a hybrid air mass modeling system, meaning we have both a mass airflow sensor that's used to measure the amount of air mass. We also have speed density. Speed density is used to estimate the amount of air mass coming into the engine. Now, a lot of OEM manufacturers are redundant in their airflow modeling, meaning they have both a measurement of airflow and then an estimation of airflow. Now, we do this if we have a mass airflow sensor fail, we have a backup mode so we can run off of the MAP sensor. We also do the hybrid mode, or the OEMs choose to do the hybrid mode, because they need to have a backup air mass registration in order to characterize the airflow coming into the engine, the air mass coming into the engine under a transient condition. Thanks for checking out our teaser clip. If you want to see the rest of this video and more than 500 hours of current EFI training we have to offer, make sure you click right here. If you want to go and check out more teaser clips from this training course, click here, and you don't want to miss any of the videos we're going to be releasing on this channel, so make sure you subscribe and click here. Thanks for watching, and I'll see you guys later.